start natural magnetism.
So we have to note the question.
No, just write the question number. You have written the question number? No. Yes, Ahmed. Did you write the question number? No. 7.25.
Yes, sir.
7.25. Okay, this natural magnetism natural magnetism. This is chapter number 5 of NCRT. Very small topic, very small chapter, and we're very less weightage with respect to your board's exam. The natural magnetism starts with the concept of bar magnet. Or let's see first the difference between the magnetics that we did in chapter number 4 and natural magnetism. In magnetics, we studied the magnetic effect of current. Like we studied when current passes through a wire, then that wire can generate magnetic field. That we did in magnetics chapter number 4. In natural magnetism, we usually deal with natural magnets. Natural magnets, permanent magnets we deal with. Now you don't require current to generate magnetic field. Now you have permanent magnets. For example, you can have a bar magnet. You study the properties of bar magnet. You can have a horseshoe magnet. Shazada, are you in class? Or you can have horseshoe magnet. Horseshoe magnet is also a type of permanent magnet. So now we will study the properties of a permanent magnet. Along with permanent magnet, you will also study earth magnetism. Very small topic. It's more geography than physics. In earth magnetism, you will study the magnetic field of the earth. These are the two major parts of the chapter. One is the study of bar magnet, permanent magnet, and the second one, earth magnetism. So the story of bar magnet, we'll first study what is a bar. See, bar magnet is a permanent magnet. It's a permanent magnet. See, this chapter is very theoretical. It's permanent magnet, but it is artificial. You create bar magnet artificial. Next, we have few properties of bar magnet. Next, we have properties of bar magnet. The first property of bar magnet is its attractive property. It can attract pieces of iron. It can attract small pieces of iron. That's one property of bar magnet. It can attract small pieces of iron. It's a very dry topic. So this is a bar magnet. This is North Pole. And this is South Pole. It can attract the pieces of iron to its poles. The second property is directive property. Directive property means if you take a freely suspended bar magnet, it's a freely suspended bar magnet. Like you take a bar magnet, connect this bar magnet with thread and release it. Whenever you release this bar magnet, this will come to rest in north-south direction. Whenever this bar magnet comes to rest, its north pole is towards the north pole of Earth and its south pole is towards the south pole of the Earth. This is the directive property. Using this property, you can decide direction with the help of a magnet. That's known as directive property. Like whenever this bar magnet comes to rest, its north pole is towards the geographic north pole and its south pole is towards the geographic south. This is what we call the directive property. Third property is, so you can say that freely suspended magnet. Always align in north-south direction. Means the north pole of the magnet, it's towards the north pole of Earth and south pole of magnet, it's towards the south pole of it. Note it down. Yes, written. Can I scroll it? Fatma, we
Yes,
just
sir.
have started this chapter, huh? Last chapter, chapter number 5 of the first book.
Sir,
Yes.
so what do you mean by permanent magnet but it's artificial?
Permanent means to get the magnetic field, there is no need to supply current now. It's artificial because it's generated by, say, how we generate bar magnet. You take a piece of iron, you connect this piece of iron to source of current. When current passes through this piece of iron, this piece of iron gains some permanent magnetic field. Now it becomes a magnet. But it gains magnetic field through an artificial method. It's not a natural magnet. It doesn't occur naturally. It's permanent in the sense to get magnetic field, there is no need to further supply the current here. In that sense, this is permanent. It's artificial because it's not occurring naturally. You are passing current through this iron piece to convert it into a magnet. Okay, Mariam?
Yes.
Now write the properties. From examination point of view, this chapter is least important. No, actually, the north pole of the Earth behaves as a magnetic south pole. The pole that you call geographic north. The property of geographic north is like the south pole of a magnet. And the property of geographic south is like the north pole of a magnet. That's why it happens that north of Earth will attract the north of the magnet and south of Earth will attract the south of the magnet. We'll do this thing in detail in Earth magnetism.
Okay, sir.
But this is how we decide direction using a magnet. Okay, third property, a very general property. This Shahzada will tell. Shahzada, still in class? Shahzada is not in class. Nazira. Nazira, just tell me, can magnetic poles, can monopoles exist? Like, can we have an I take a magnet? Huh? I take a magnet, bar magnet, north pole of the magnet, and this is the south pole of the magnet. If I cut this magnet into two parts, can I get isolated north pole and isolated south pole, Nazira?
No, sir.
So what will happen?
This will create a new magnet.
It will create a new magnet. It will create new north pole and south poles. Huh? So you will always have, when you break it from here, you will always get dipole. No matter how you break this one, you'll always get dipole. So you can say that magnetic poles always exist in pairs. You can say that magnetic poles always exist in pairs. So monopoles does not exist. What always exists is a dipole. The combination of north pole and south pole always exists. Dipole always exists. Monopoles do not exist in magnetism. The last property is known as magnetic induction. Magnetic induction. Magnetic induction means, have you ever observed, like if you place a needle in contact with a magnet, after a few hours or after some time, the needle becomes magnetic. It starts behaving like a magnet. Have you observed this thing?
Yes, sir.
Like if you take a needle or you take a scissor and you, or a screwdriver, you place that screwdriver in contact with a magnet for a very long time, then that screwdriver, that needle, that scissor become magnetic. That property of magnet, through which if you place a iron piece in contact with the magnet, the iron piece becomes magnetic, is known as magnetic induction. So magnetic induction means magnet induce magnetism in a magnetic substance. Magnetic substance means substance like iron, ferromagnetic material. Iron, cobalt, ferromagnetic material. So if you place a ferromagnetic material like iron in contact with a magnet, after some time, this iron starts behaving like a magnet. This is known as magnetic induction. Note it down, these two properties.
So can you show the first and second properties?
Mhm.
So the properties.
Properties. See, next, some characteristics of a magnet. The next are few characteristics of a magnet. The first is pole strength, or you can say magnetic poles. Magnetic pole means north pole and south pole. So if you take a magnet, this is the magnet. The magnetic poles does not lie at the corner of the magnet. They lie a bit inside. Like if this is your magnet, bar magnet, then your magnetic poles does not lie here. Your magnetic poles lie here. This is the north pole and this is the south. To remember this. So you can say poles of magnet lie somewhat inside the magnet. Inside the magnet. Not at geometrical ends. Like these are the geometrical ends. Magnetic poles does not lie at the geometrical ends. They lie a bit inside. That's magnetic poles. After magnetic poles, there's another characteristic which is known as magnetic axis. Magnetic axis simply means a line passing through the north pole and south. Line passing through north pole and south. So the line which is passing through the north pole and the south pole is known as the magnetic axis. So this is the north pole. This is the south pole. So the line is passing through the north pole and south pole. We call this line as magnetic axis. This is the magnetic axis. Third part. After magnetic axis, we have magnetic equator. This chapter have too much definitions. Magnetic equator. Magnetic equator means it's a line which is perpendicular to magnetic axis. Magnetic equator is a line perpendicular to magnetic axis. Like this is north pole, this is south pole, this is the magnetic axis. So a line perpendicular to magnetic axis is magnetic equator. This is magnetic equator. A line passing through center of magnet and perpendicular to magnetic axis is magnetic equator now. After magnetic equator, we have another thing which is known as magnetic length. From this magnetic length, you can get conceptual questions. See, what does magnetic length means? Magnetic length is just the separation between the magnetic poles. This is north pole. This is south pole. This separation between the north pole and the south pole is known as magnetic length. So this is separation between magnetic poles. So Ahmed, if I compare this magnetic length with the geographic length, this is the geographic or geometrical length. This is the geometrical length. This is geometrical length of the magnet. So Ahmed, what do you think? Which one is greater? Geometric length or magnetic length?
Geometrical length.
Geometrical length. Should always remember that magnetic length is always less than the geometric length. It's always true. Like magnetic length is always less than the geographic length. Okay, note it down.
Sir, can you scroll up?
Mhm. So these were just definitions. After definitions, the next topic you can do in magnetism by comparison with electrostatics. Like whatever we did in electrostat, we studied charge, we studied Coulomb's law, we studied dipole, we studied electric field on the equatorial line, axial line, torque, potential energy. As it is, you can write those terms for magnetism also. So now we will do the rest of the magnetism using by comparing it with the electrostatics. The best way to do magnetism. So comparison between electrostatics and magnetism. So this with this comparison, we'll finish bar magnet. So this is electrostat. Electrostatics. And this is magnetics. or sometimes it's known as magnetostatics. See, 70% things in magnetostatics are based on hypothetical North Pole and hypothetical South Pole. So you can say that a big part of magnetostatics is hypothetical because isolated North Poles and South Pole does not exist. And that is not given in NCERT. I'm starting from the scratch, but at least the 50% of what I'm discussing is not in NCERT. But you will need that basic to understand the the concepts which are given in NCERT. So electrostatics starts with the concept of electric charge. So we have two types of charges, positive charge and negative charge. SI unit is Coulomb. In magnetostatics, just like electrostatics, you can use a term which is known as magnetic charge, sometimes known as magnetic pole strength also. Magnetic pole strength also. We represent it by small m. There are two types of poles, North Pole and South Pole, represented by. Its SI unit is ampere meter. SI unit is ampere meter. Now, after electric charge, the next quantity is electric dipole. What is electric dipole? Fatma, do you remember what do you mean by electric dipole?
Positive charge to negative charge.
Yes, electric dipole is a system which have equal amount of positive and negative charge. Same amount of positive and negative charge is dipole, equal amount of positive and negative charge. Just like electric dipole, we have magnetic dipole. So what is magnetic dipole? The system having two types of pole. One is North Pole and another is South. That's a magnetic dipole. It have a North Pole and a South Pole. That's magnetic dipole. Electric dipole have equal amount of positive charge and negative charge. Next, we have defined something like electric dipole moment. The length of the dipole we represent it by 2a. Instead of charge, we are using m for magnetic pole strength 1 and magnetic pole strength for South. Here the length is represented by L. Electric dipole moment. Abdullah, do you remember expression for electric dipole moment?
Sir,
Yes, Abdullah.
P is equals to PQL.
Q into 2a. Electric dipole moment is charge multiplied by separation. Electric dipole moment is a vector quantity. Its direction is from negative to positive charge. Just like electric dipole moment, we have a quantity here which is known as magnetic dipole moment. Magnetic dipole moment. So Fatma, can you guess the expression for magnetic dipole moment just by comparing, just writing the analog of Q and 2a? Instead of charge, what we use in magnetism, Fatma?
Pole strength M.
Pole strength. So instead of Q, you will use M. Instead of 2a, we are using L. So that's its SI unit is Coulomb meter. Its SI unit is ampere meter square. This is the magnetic dipole moment. Its SI unit is ampere meter square. Fourth quantity.
So what about Tesla?
Tesla is for the magnetic field, not for the magnetic dipole moment. Tesla is the unit of magnetic
Yes.
field. After electric dipole moment, see this is something important for conceptual questions. You can get many conceptual questions from this topic only. After electric dipole moment, we have expression for electric field on axial line of dipole. Electric field on axial line of dipole. Does anyone remember what we mean by axial line? Noor.
Sir,
Yes, Noor. What do you mean by axial line of dipole?
On the line of the dipole.
On the line of the dipole. Like this is the line of dipole. Huh? On the line of the dipole is axial line. And Noor was the expression of electric field on the axial line?
1 by 4 pi epsilon into 2p by x square.
R cube. 2 pi 4 pi epsilon naught R cube. It goes as 1 by q. So just like electric field axial line of electric dipole, you can have electric field on the axial line of magnetic dipole. You can have magnetic field on axial line of magnetic dipole. So wherever I'm writing magnetic dipole, you can write bar magnet or any source of magnetic field, because every source of magnetic field is a dipole. So if I take this bar magnet, south pole here, north pole here, and I ask you to calculate the magnetic field over this point. Let's say the separation from the center of the dipole to here is R. So if I write just the analog, it's B is equal to 2P. Instead of dipole moment, what we will use here, Mariam? Which term you will use here instead of dipole moment?
Magnetic dipole.
Magnetic dipole moment, 2m. Divide, instead of 1 over 4 pi epsilon naught, which term you will use? Nazira? Mu naught by
4 pi.
4 pi into 2m over R cube. After this, the fifth one. Electric field on axial line. And remember the direction of, see, this is the direction of magnetic movement from south to earth. And same is the direction of magnetic field. So you can say on axial line, direction of magnetic field is same as that of dipole. Is same as that of dipole. Then we have fifth, electric field on equatorial line. Electric field on equatorial line. Yes, direction of magnetic dipole moment is from south to north. It's south to north. So we can write it here. Direction of M is south to north. Electric field on equatorial line. Like this is the electric dipole. It's minus Q. Yes.
So that was capital M or small m, which you wrote above now?
Capital M.
Capital.
Magnetic moment is capital M. Small m is pole strength. It doesn't have direction. So this is the equatorial line, the perpendicular bisector. So over this point, what was the expression of electric field here? Does anyone remember? It's minus P over 4 pi epsilon naught R cube. If you write the same expression for magnetic field, same thing for magnetic field, then this would be like magnetic field on equatorial line of bar magnet, you can say. Bar magnet or any magnet. So you take a bar magnet, North Pole, South Pole. I take this point here, perpendicular bisector. This separation is R. The expression of magnetic field will be like point to point minus. Instead of P, you can write M. Instead of 1 over 4 pi epsilon naught, you can write mu naught by 4 pi. Into R cube with a negative sign. This negative sign simply says, what's the direction of magnetic moment, Ahmed? North to south, south to north. What's the direction of magnetic moment?
South no.
South to north. This is the direction of magnetic moment from south to north. So see, magnetic field and magnetic moment are in opposite direction. So you can say that magnetic field is in this direction. B and M are in opposite directions. After fifth, then it is sixth part. So we have electric field on equatorial line, magnetic field equatorial line of bar magnet. After this, we have torque on electric dipole in uniform electric field. Let's do one thing, just note at least up to point number 5. Then I will start 6 and 7. Note it down. So this is a good revision of electrostat also.
Sir, can you scroll up?
Yes, Noor, but that is for a coil. This is for a bar magnet. Huh? That NIA is for a coil, for a current carrying coil. But this relation M into L is for a permanent magnet.
Sir, can you scroll up?
Mhm.
Yes, sir.
Okay. Okay. The next is the expression of torque. Sixth point. Torque on electric dipole. Torque on electric dipole in uniform field. Like if you take a uniform electric field, this is uniform field. And this uniform field, if you place a dipole, means a system having a negative charge minus Q and a charge plus Q. This is the dipole moment. And the angle between the dipole moment and the field is theta. So it will experience a torque, and that torque is P cross E now. And the net force on the dipole is 0. If I repeat the same thing with magnetic dipole, torque on magnetic dipole in uniform field. Magnetic dipole means bar magnet. So if you take a uniform magnetic field, and in this uniform magnetic field, if you place a bar magnet, this is south pole and this is the north pole of the magnet, this is the direction of magnetic moment. Okay. This angle is theta. This too will experience a torque, and that torque will be M cross B now. Net force will be 0. This is it. Let's note it down. Yes, Abdullah, class over. So most probably on Thursday we'll finish this chapter. And then we will decide whether we want to do revision or should start with optics.
It's a revision.
Revision. Yes,
Sir,
that
can
we
you
will.
show the fifth one?
Yes, yes.
Thanks,
Thank you.
sir. Thank you, sir.
Sure.
Thank you, sir.
Sure. Okay, Allah Hafiz.
Thank you, sir.
Sure. Okay, Bashar. Allah Hafiz.